the temperature, and in your in negative temperature coefficient, your resistance will get decreased if you increase the resistance. So, but we did not discuss the graph, okay, of positive and negative temperature coefficient. So, if you want to draw the graph of positive and negative temperature, so here you will get temperature, okay, here you will get temperature. And over here you will get resistance. That resistance will be in kilo ohm. So your, let's say I am drawing positive temperature coefficient, okay, and I am taking an example, and that is metal. So for metal, my curve will be like this, okay. So it means that if my temperature is 0 degree,
then the resistance will be that.
Yeah, there is some sort of resistance. There is some sort of resistance, okay. That is the y-intercept, okay. Okay, and the curve for
what does positive temperature coefficient and negative temperature coefficient mean? So if the gradient is negative, then if it's like this, then that's negative, right?
Yeah, so it will be like this. Let's say I'm drawing for thermistor, okay. So for thermistor, it will be like this.
Oh yeah.
Actually, this curve will give us an inverse relation, okay.
Why is the not like that? Why is it straight?
It's like that. If you increase the temperature, then your resistance is getting decreased. Okay, if you draw it like this, then here if you increase the temperature, then the resistance will get increased.
No, I'm talking about the green line for the conductor.
Yeah, this is for the metal.
Yeah,
and metal have positive temperature coefficient.
But why is it straight line? Why is it not like this?
So it is a straight line. It means that if you increase the resistance, if you increase the temperature, then the resistance will increase proportionally.
Why proportionally? How come for thermistor it's not proportional? It's for thermistor the rate of decrease will slow down over time because it gets less heat.
Yeah, so thermistor is a semiconductor. Okay, so maybe it is maybe the number of atoms will be different, so that's why it's showing curve-like behavior. And maybe maybe all atoms are same in metal, so that's why it's showing. So that's why the effect of temperature on each atom is same.
Oh, so what atoms is contained in the thermistor?
That is the semiconductor. The material is semiconductor in thermistor, and this is for thermistor. Okay, I'm writing all this because I am going to save all these slides, so that's why.
Oh, like for example here,
this is thermistor.
Let me show you. This is the valence. This is the conductor.
Yeah, that is the conduction band. So
in the thermistor, these are the electrons, and only some of them will jump here. That's why it's like a curve. But in the metal, all of them will flow. Not some of them. All of them will jump. I don't know how to explain it.
Okay. Okay. So wait. In conductor, that is like okay. Well, if this is my in conductor, okay. This is EC. This is the energy. Okay. This is EC, and over here I have EV. Okay. So here we have lots of electrons, and that's required and here we also have some electron in conductor. So this electron required a very small amount of energy. So if you give this electron a small temperature, if you give this electron small energy, so it will jump over here. So it will become a conductor. And in insulator, the gap will be like,
that's why it's a straight line, because all of that.
Yeah, but in semiconductor, it will be the gap will be in between metal and in between conductor and insulator.
Yeah, so only some of them will jump. Not all of
them. But in semiconductor, there is no electron at room temperature over here.
Yeah.
So, but if you increase the temperature, and that temperature give this electron such an energy that is greater than this much energy.
But how do you increase the temperature initially then? How do you start it off?
What do you mean by increase? How you will increase it?
How do you increase the temperature without
What?
without increasing the temperature?
How you will increase the temperature without decreasing the temperature? Okay. So is this the question? Yeah, is this the answer?
Do you get what I mean?
Okay. So if you increase the temperature and the energy, if you increase the temperature, it means you are giving energy to this electron. And if that energy is greater than this much energy, this much difference, that is equal to EC minus EV. Okay, this is EV.
Voltage.
Valence band.
Okay.
Voltage. This is the conduction band. Okay. Acha, and normally in diode, okay, if you have only one PN junction, then this voltage is 0.7 volt.
Okay.
Yeah, that is the 0.7 volt. So it means that you will require this much of energy to each electron, 0.7 joule energy per coulomb. Actually, voltage is equal to energy per coulomb. So it means you need to give this electron 0.7 joule of energy. Each electron. Okay, this will be 0.7 if your material is made up from silicon. Okay, if your material is made up from silicon. If your material is made up from silicon, and if your material is made up of germanium, then that's voltage will be 0.3 volt.
Yeah, got it.
Germanium. Is germanium GE or GA?
GE.
GE, that is the gallium. GA is the gallium, I think. Am I right?
Whatever. Let's not go into chemistry, please.
Yeah, but
Have you finished the chapter in the book? It's taking so long.
No. Today in today's class, I will finish this chapter.
Finally.
Okay, so okay. Okay, so you know what is mean by series resistance and parallel resistance? How you will calculate the series resistance? Okay.
Yeah,
And okay, yeah, okay, that is easy. But I have a small question in that topic for you, and that is why we are going to make a connection, make a series and parallel connection.
in parallel.
Huh?
What's your question?
My question is why we are going to make a series and parallel connection of resistance.
Why we're going to make what? Series?
Series and parallel connection of resistances. Parallel. Huh?
What do you mean? Like series
Okay,
and parallel?
Okay, so if three resistors are connected in series like this, then why we are going to make the series connection of resistance or parallel connection of resistance?
Oh, that's easy because in series, if this breaks, then all of them breaks. In parallel, one breaks, it won't affect the rest.
Okay.
And also because in parallel, the total resistance is less, smaller because it's 1 over our total.
Yeah, so your total resistance is smaller than the greater resistance. Okay. I know you know all the resistance, all the relationship. Okay, so if this resistance, okay, if this resistance is 1 ohm, this resistance is 3 ohm, and this resistance is 2 ohm. And you, okay, very good. And you also have, lots of other resistances. Okay, and that is 2 ohm. This is let's say 1 ohm, and this is also 1 ohm.
Mm-hmm.
But my one requirement is that I need 8 ohm resistance, and my second requirement is that I need 0.5 ohm resistance. So how you will fulfill my requirements? If Farjana is now in the laboratory and he is making some sort of connection of the resistances, so how you will fulfill my requirement? How you will fulfill the requirements of any other customers?
Wait, what's the question? You want 1 8 ohm resistor and 1 5 ohm resistor connected in parallel?
1.5 ohm resistance. 0.5 ohm resistance. This is 0.5.
Yeah.
So I need 8 ohm resistance. So how you will make a connections?
Oh, it's two separate questions. Number 1, number 2. Okay.
Yeah, number 1, number 2. Yes.
Okay, fine. How am I supposed to do this in my head? This is impossible.
It is possible.
Okay, wait.
Okay. Okay. So we make a series connection. We make a series connection if my requirement is greater than the greater resistance. If my requirement is greater than the greater resistance. So which resistance? Which resistor is have a greater value?
3.
3. Okay, 3 ohm have a greater value. Okay, but my requirement is 8 ohm, so I will make a series connection of 3, 4, 5, 6. I will connect another that is 7 ohm, and then another that is 8 ohm. Or you can make 1, 2 ohm resistance. Okay, so series connection give you the resistance, and that resistance will be greater than the greater resistance of than the greater resistor.
Always.
Yeah, always. Yes, always. And parallel connection will give you the resistor, will give you the resistance, and the value of that resistance will be less than the smaller value of any resistance. If this resistance is 1 ohm, this resistance is 2 ohm, this resistance is 3 ohm, smaller resistance is 1 ohm, but this equivalent resistance or equivalent will be less than 1 ohm.
What if you want a resistance between 1 and 3? Then you have to do a mixture of parallel.
You will. Let's say you require your requirement is 8.5 ohm. Okay, so through this I will get 8 ohm resistance. Here I will make a parallel connection of 1 ohm resistance.
How do you know?
Because if you make the 1 by R equivalent, that should be equal to 1 plus 1, that is equal to 2. So your R equivalent will be equal to 1 by 2.
What if it's 9 ohms?
If it's 9 ohm, then I will make another resistance over here of 1 ohm. That will give me 9 ohm.
Wait, where are you connecting this? If it's 8.5 ohms, where are you going to connect this?
Okay, where?
This.
You will connect there. Okay, I'm going to save it.
Wait, let me clear it. Wait. Yeah, no.
Okay, so I will make that connection over here. I will make that connection over here like this. Okay, that should be 1. Okay, your requirement is 8.5 ohm, right? So this will be 2 ohm, 2 ohm, 2 ohm, 2 ohm. So from this I get 8 ohm resistance, and over here I will make a 1 ohm resistance in parallel. So this AB will give me 8.5 ohm. So our AB is equal to 8.5 ohm. And also, if you want to calculate the equivalent resistance, then if there is 2 equivalent resistance, if there is only 2 resistors, okay, then your R equivalent, that will be equal to R1 R2 divided by R1 plus R2. Okay.
What? What does R equivalent mean?
Equivalent means that the equivalent resistance of the parallel connection of these 2 resistors. That will be, in this case, that will be 0.5. Like R equivalent, that will be equal to R1 R2 is 1 ohm divided by 1 plus 1 is 2, so that will be equal to 0.5. So it means that it means that this portion will give you 0.5 ohm resistance. That is the R equivalent of the parallel connection of these 2 resistance. Okay, and also if your okay, if the resistance is same, okay, if the resistance is same, okay, this is one point. You should remember these points. If all resistors have equal value, then your R equivalent will be equal to value of one resistance, okay, and divided by number of R resistance. In this case, that is 2 resistance and that have same value, so divided by 2. And the value of one resistor is 1 ohm, so that should be 1 by 2 ohm. If they are like this,
only if it's equal, right?
If they are like this, 3 and each value is 2 ohm, 2 ohm, 2 ohm, then your R equivalent, that should be equal to 2 divided by 3.
Yeah,
That is 3. 0.5, no 0.6, 0.66.
Yeah.
You will get 0.66 ohm. Okay, and you can also check it like 1 by R equivalent is equal to 1 by 2 plus 1 by 2 plus 1 by 2.
Yeah.
That should be equal to 3 by 2, and that should be equal to 2 by 3.
Yeah. So the the 1 over RT equals 1 over R1 plus 1 over R2. Is that the same equation as this?
Yeah, yeah, that is the same equation. But you will you will only use this type of equation if you have only 2 resistances.
Yeah.
But if you have 3 resistances like this, then you will
Yeah, I know. We use the other one. 1 over RT equals 1 over R1 plus 1 over R2.
No, your R equivalent that should be equal to R1, R2, R3 divided by R1, R2 plus R2, R3 plus R3, R1.
Yeah, same thing as the one I said.
Yeah, let's check it. Yeah, so this type of equation will be easy for you instead of this. It will,
That's
yeah, that will waste lots of your time. And if same resistances is given to you and that are in series, okay, like this. Sometime in exam they said that you have 500 resistors, and each resistor value is 6 ohm. Calculate the equivalent resistance. So you will only multiply 500 times 6. So that will give you equivalent resistance. Okay, instead of adding all these.
Yeah.
Okay. Okay. So okay. We already studied that potential difference, or you can say that the voltage, that is equal to energy per unit charge.
Yeah.
Okay. So, and I also already explained this in last tutorial, that if you have a resistor, okay, and this is the battery. Yeah. So this charge will bring energy over from this battery, and it will dissipate that energy to this resistor. Okay. So it means there is a loss of energy in this resistor. Okay. Okay. So you can say that the potential drop in this component, you can call that the potential drop.
Oh, that's why you need to connect the voltmeter in parallel.
Yeah, that is the potential drop. So yeah, if you want to calculate the voltage across this component, then you will connect a voltmeter in parallel with it. So there will be a potential drop. Then you can represent and so if there is a potential drop in any component, you can call that component as the passive component.
Isn't that any component? All components are.
And the sign convention will be over here. This side will be your positive, and this side will be your negative, because there is a loss of energy. If you move in this direction, there is a loss of energy in this component. So that's why it is called potential drop or passive components, and the sign convention will be like this.
But all components have a potential drop.
No. So electron will lose energy, okay, and it will come over here, and it will go back to the battery. Okay, here this electron will get energy, okay, and will go again and will follow this path. So there is an increase of energy. There is a potential rise. So that's why it is called potential rise. And that's why it is called active component.
Yesterday you explained to me why voltmeter is connected in parallel. Yeah.
Okay, wait.
I forgot.
Okay. Note all your question on page, so I will clear all your confusion at the end of this lecture, because I want to complete your this chapter in this today class. Okay. Yeah, and there is also a final limitation, and that final limitation is the second. So that's why I can't do anything. And nowadays Ramzan is a bit tough. Okay. Yeah. So that's why the convention will be like this. Okay, over here I will put negative sign, over here I will put positive sign, because there is an energy rise. So that's why this is called potential rise or active component, or you can say that is the battery. Okay. So hopefully you studied all these piezo and active component in KVL, Kirchoff voltage law.
No, I've never. Wait, can you quickly explain?
Yeah.
Can you
So
quickly
yeah. Okay. So your question is why we are going to connect the voltmeter in parallel. Okay. So you can connect the voltmeter across this potential like this. If you want to, if you want to find the voltage of the battery, okay, so you can connect the voltmeter in over here. But the question is why we are going to measure the potential difference. Sorry, why we are going to put the voltmeter in parallel? This is your question, right?
Yeah.
Okay, so actually voltmeter give me potential difference, okay, and we can only calculate the potential difference if we connect the terminal at different potential. Here we have positive potential, here we have negative potential. Energy at this point is higher, energy at this point is lower. So there is a potential difference. So that's why voltmeter give me potential difference, voltage, okay, and we must keep the resistance of this voltmeter infinite so that no current pass across this voltmeter. All current will pass across this. Yeah. So if there is a small amount, if there is some current which pass across this way, then there will be a heating effect. Yeah, there will be a heating effect, and that will destroy my voltmeter.
And it will also affect the results because the voltage calculated would be
Yeah.
greater than expected.
Yeah, and that will also affect my voltmeter. Okay. Why we are going to connect the ammeter in series? Because we want to calculate the current, all current which pass across this ammeter. Because if we connect this ammeter in series, then that is the only way through which we can get complete all current.
Yeah, but you know if there's a heating effect, would that increase the voltage result or decrease the voltage result shown on the voltmeter?
If there is no heating effect, then what?
If there is a heating effect, if there's a heating effect,
Yeah.
how would that affect?
If there is a heating effect, then that will destroy your voltmeter.
No, but before destroying the
Yeah,
voltmeter.
actually, yeah, okay. Before this, if you said that there is a heating effect, but that is not too much, okay. So that will affect your reading because there is some sort of current over here. There is some sort of current, and we don't need this current because now here electron have energy. Okay, let's say there is 50 joule. So electron want to dissipate all 50 joule energy in this resistance instead of dissipating that over here.
So the voltage reading would be less than expected because not all of the energy is being.
Yeah, the voltage will be, because some joule of energy will flow across this. Okay, so
we save this and then we can go on to the Kirchoff's voltage rule.
If this is the battery, and here we have one resistance, and last class I told you that we represent the resistance like this, and you have three resistances, okay, and the voltage of this resistance is V, and the voltage across this resistance is V1, voltage across this resistance is V2, voltage across this resistance is V3, and the resistance of this resistor is R1, R2, R3. So there is a potential. Okay, so you know what you mean by KVL?
No.
Last time you said that, yeah.
I do, but I find it hard to understand.
Yeah, okay. So KVL said that your potential rise is equal to potential drop. So we put a loop like this in this, okay. I am going to apply the KVL. So for KVL, you will make a loop like this, okay. So this loop saying that if you go like this, then there is a potential rise. If you go like this, there is a potential rise. And this is the resistor, which is a passive component, okay, which is a passive component. So if current is flowing like this, then this side of the resistor will be positive, this side of the resistor will be negative because there is a potential drop. This side will be positive, this side will be negative. This side will be positive, this side will be negative. So your rise of potential, potential rise, that will be equal to, because there is no rise of potential, all other potential is drop. So that will be equal to drop of potential in this resistor, which is equal to V1, drop of potential in this resistance, which is equal to V2, and drop of resistance in this, drop of potential in this resistance, that is V3. Okay.
Yeah.
And if I connect another parallel connection of resistor, and let's say that is the resistance, this resistance is different than this resistance. Let's say this resistance is R4. Then V3, then the voltage will be same, because in parallel connection we have same voltage. If the resistance is same, then we have same voltage. If the resistance is different, then still we have the same potential difference, same voltage. Okay, so
Sorry. Can you repeat this part?
okay.
Yeah.
Okay, so if there is another resistor, okay, and that resistor is connected in parallel with R3, okay, and that resistor is not R3, that resistor is different from this resistor. Okay, so that's why I give different name, R4. Okay, so if your R3 is not equal to R4, then the potential across these two will be equal to V3. And if your R3 is equal to R4, then still you will have a same potential, and that is V3, because both resistors are connected in parallel. So in this case, your current will be same, I3 will be equal to I4. But in this case, your current will not be same. I3 will not be equal to I4.
What's I3 and what's I4?
This is I3 and this is I4.
Oh. But in both cases, the voltage is the same.
Yeah, but in both cases, the voltage is the same. That is V3, because the connection is parallel.
So what is this low state? What's the low?
So KVL tell us that the potential rise is equal to potential drop. Okay, so this is the statement of KVL. So your potential rise is V, that will be equal to V1 plus V2 plus V3.
Oh, is there? Okay, fine.
Yeah, so this is too simple. Okay, and we also have KVL. There is another law, that is Kirchoff voltage law. Kirchoff current law. KCL, sorry.
No, that's what that one is easy as well.
Okay.
Of current that enters the point is equal to the sum of current that leaves that point.
But there is a small question.
Oh, okay.
Your I1 will be equal to what?
Any value.
Okay, so this law tells us that this is the junction, okay? Current entering into the junction is equal to current leaving the junction. I1
equals I2 plus I2 plus I2.
Okay. Okay, and this KCL give us the law of conservation of charge. Okay. If you are using this law, KCL, okay, if you are using this law for such like circuit, then you must satisfy this law of conservation of charge. As we know that current is equal to charge per unit time. If there is 10 charges which are moving in this direction, then 2 charges will flow like this, 3 charges will flow like this, then how much left? That is 5 charges. So 5 charges must flow like this, not the 4 charges, okay? Your law of conservation of charges means your charges entering into this junction will always be equal to charges leaving this junction. And your KVL must satisfy the law of conservation of energy. Mostly in MCQs, such type of MCQs can that KCL satisfy the law of conservation of charge or law of conservation of energy. So that is the law of conservation of charge, because current is equal to charge per unit time. So you remember it like this. And KVL is the voltage, so that is energy. So that satisfies the law of conservation of energy.
But in reality, isn't some heat dissipated from the current?
Yeah.
So
Yeah. But in reality, there is also a law of conservation. The energy is also conserved in reality.
Yeah, energy is conserved, but charge isn't conserved.
Charge is conserved.
Where does the charge go? Because, for example, like, yeah,
if there is some sort of Farjana over here, she is standing over here, then she will block the charge. That don't go over here, because I am present over here.
So is that the reality?
No, that is not the reality. In reality, the charge will be conserved, and you are talking about the heating effect, and that is the energy.
But the heating effect affects the current, not the voltage.
Heat affect the current?
Yeah, the heating. Oh wait, the current affects the heating. Sorry. The current creates the heat, and the heat affects of energy, the
Yeah.
voltage.
Yes. So
Okay, got it. Got it.
in reality, the charge will always be conserved, and energy will also be conserved in reality. If you encounter the heating effect as well, then you can calculate the energy, and that will always be conserved. But if you encounter the heating effect, and that is impossible.
What's the difference between charge and energy?
Charge is positive or negative charge. Simple.
Oh, okay.
Energy is something.
Yeah, I get it. You can't. It's not something you could just describe. Man.
Okay, so you know what is mean by electrolyte?
No.
You study about electrolyte. Maybe you study about electrolyte in your O level. Yeah, maybe in your chemistry.
No. Oh. Is it for electrolysis?
Yeah, electrolysis. So over here I have a anode, and over here I have a cathode.
Oh, cathode.
Yeah, and hopefully you studied about that how electrolysis is occurring in NaCl. So I am not going to go in depth in all these theories. Okay, so over here I have a positive. So let's say here I have. So let's say this is my anode, and on anode I have.
The anode will attract the chloride ions.
Okay, and anode have which charge? Anode have negative, positive charge.
Yeah.
And on cathode we have negative charge. Okay, so there is some sort of, okay, so here we have lots of Na ions, and here we have lots of minus ion. Okay, and electron will come over. Here we have lots of electron, and here we have lots of positive charge. Okay, so electron will flow like this. Okay, or sorry, this electron will leave this electrode. Okay, and it will come over here, and Na, I think Na will attract that electron and will come over here. So if there is, so this electron will feel some sort of resistance over here. He will feel some sort of hurdle over here in this fluid, which is present inside this beaker. Okay. So that resistance, that hurdle is known as the internal resistance. So internal resistance is the, so internal resistance so internal resistance of this source of electricity is due to the opposition to the flow of charges. Okay, so internal resistance give you the resistance which this electron inside the source will feel. And over here I get a potential, and that potential is V. That potential is V, and that is voltage. But there is also another term that is known as EMF, electromagnetic force, no, electromotive force. Yeah, so what do you mean by EMF?
What's the definition of internal resistance? Proper definition. In the exam, they always ask. Oh, it's fine. We'll check that later.
Yeah, internal resistance is the resistance which electron feed inside the source.
Oh, cool.
Yeah, you can say that internal resistance is the resistance of the source. Simple.
Yeah.
Okay, simple. Internal resistance is the resistance of the source. Okay, so now let's convert this practical into an electrical circuit.
Yeah.
So in circuit, I have potential, which this will get, so that is represented by this. And I also have some internal resistance, and the value of that resistance is small. Okay, so that's why I am represented there by R. Okay, and this potential is EMF. Okay, so here I will get a voltage, and that is V. So this is the volt. This is known as voltage or potential difference, you can say, because in this is the, okay. So the EMF is the actual energy. Okay.
Yeah.
If your potential is like nowadays we get cells, that is 1.5 volt. Okay. So it means that if there is some sort of internal resistance, that this EMF will be greater than 1.5. because there is some sort of dissipation of energy in this internal resistance. So now I am going to calculate the EMF. Okay, I am going to calculate the EMF. So EMF is the potential. So that's why I will use KVL Kirchoff voltage law, because I am going to calculate the voltage. So the first step is I will make a loop that is like this. You can make loop clockwise or anti-clockwise. Okay, so let's say I'm making loop clockwise. So if you see over here, this is negative, this is positive, this is positive, this is negative, and over here I get positive because this is positive potential. So here I will do positive and this is negative. So if you move like this in the clockwise direction, so there is a potential rise. So potential rise is EMF, and that is equal to, there is a potential drop. So, and let's say the current in this circuit is I. So that should be equal to IR. Yeah, voltage across this small resistance. Let's say that is V small r. And there is also a potential drop. Okay, potential drop. So plus V.
Yeah.
If the current is I, then your EMF, that will be equal to IR plus V.
Yeah.
So your EMF is equal to IR plus V.
Yeah.
Okay.
Do you count the internal resistance as well?
Yeah.
Do you take into account the internal resistance of the source?
Yeah, I take into account the internals of the source. And let's say here I have a load. Okay. Let's say I'm also taking a load over here. Let's say I have a load.
Oh, this is the source. Yeah.
Yeah. So this is the source. Okay. This is the source. And let's say here I have a load, and the resistance of that load is R. Then here I will get IR. Here I will get IR. Okay. So
what does load mean? Load is any component, right? Bulb, motor.
yeah, load is the passive component. Load is the dissipative component. Okay. Okay, so your EMF is equal to IR, I capital R plus I small r.
Yeah.
So your EMF, that is equal to I capital R plus I small r. Okay. Now I am going to multiply I with this equation. So I will get like this. Let's say EMF is I. So here I will get I. Okay, I am multiplying by R. This will be equal to I square R plus I square small r. So this gives me that your power supplied by the cell, this will give us a power supplied by the cell, that is equal to power dissipated, power delivered to load.
Yeah.
This is the load. So power
by load or delivered, same thing.
Power delivered to load, in load, and power wasted in the cell.
Yeah. So the EMF is the work done on the electrons.
Okay, sometimes you feel that if you take a cell, okay, and after some sort of operation, it will heat up, okay, it will be hot. If you take a cell, it will be hot, and that hotness is because of the internal resistance, okay.
Yeah.
So so your power supplied by the cell is equal to power delivered to in load and plus power wasted in the cell. So this is the power wasted in the cell, this is the power delivered to load, and this is the power supplied by the cell. Okay. Okay. So over here, my current will be equal to, okay, my EMF, that is equal to IR plus I capital R. So my current is equal to EMF divided by R plus capital R. Okay. So and my load is this. This is my load. Okay. And the resistance of the load is R. So the power dissipated in this load is equal to P is equal to I square R. Okay, capital R. So my power will be equal to I is equal to E. So that should be E square divided by R plus R whole square and this R.
Yeah.
Okay, so if you draw a graph of power and load resistance, if you draw a graph of power and load resistance,
Wait, how did you get this equation?
wait. And this is the power. So your curve will be like this. If you increase the load resistance, then your power will get increased. But then it will get decreased.
Oh.
Okay, so over here you will get a maximum power. At this stage you will get a maximum power, and that and over here your resistance will be equal to the internal resistance. Your this load resistance, which is equal to R, that's equal to your internal resistance. So your maximum power, if you want to calculate the maximum power, then your maximum power will be equal to E square. As on maximum power, my internal resistance is equal to load resistance. So this R will be equal to this R. So that will be equal to R square into R. So your maximum power, that will be equal to E square divided by R. Okay, so you can say that the load is matched to the source. Okay, when this condition is written, then you can say the load is matched to the source. So practically, if you want to get a maximum power, then you will tune your internal resistance, external resistance, and will equalize that resistance. Okay, so if your external resistance is equal to the internal resistance of the battery, then at that condition, you will get a maximum power at the output.
That's impossible to make the internal resistance that high.
Practically that is impossible because your internal resistance is not constant. Practically, your internal resistance is not a constant value.
Yeah.
Because
how do you get this equation here?
So I get this equation just to teach you that how you will get the maximum power.
How did you get from here to here?
From where to where? Actually, okay. Wait, I will draw it completely so that you will understand. Okay, so this is your internal EMF. This is your internal resistance, and this is the battery. So here you will get output. So the current is I. This is the resistance R, and this is small resistance. This is E. Okay. So power. If I said that calculate the power dissipated in this resistance R. Yeah. If I ask you that calculate the power dissipated in this resistance R, so you will use this equation that your P is equal to I square R, small r. If you are interested in this resistance.
Power of what?
Last time I discussed this, that your power.
Yeah, I know that, but power of what?
Power of what? What do you mean by power of what? It means that power dissipated in this resistor is equal to this value, I square R.
Oh, right.
Yeah, and power dissipated in this resistor is equal to I square R, and your I is equal to E by R plus R. And we get this from this, and we get this from KVL.
Oh, I get it now. Sorry, I just needed that.
Yeah. So. Okay. So this is a last minor topic.
Wait, so you know this graph, is it the same shape for every component?
Yeah, it is the same shape for every component, for every passive component, for every resistor.
So to find the maximum power, we have to create internal resistance that is.
Yeah, that must be equal to your internal resistance must be equal to the external resistance. and that is known as matching. That is known as impedance matching. Okay.
And will it not be 2R here? Not here will be 2R.
Impedance matching. That is what?
Yeah. Yes. Will it not be 2R here? 2R squared. Because here it will be R plus
Sorry,
R.
sorry. Yes. That's why this equation looked different to me. That this equation was a bit different. Okay, so this will be, yes, good. So this will be equal to R. So that will be equal to 2R, capital R, and if you take the square, so that will be equal to your P maximum.
But I don't get why the load has to be matched to the source.
Huh?
Why? I don't get this. Yeah.
So if you increase the load resistance, then your power will increase.
Oh.
And then your power will get decreased. If you increase the...
But how do you know that? How do you know this point is equal to R? How do you know R must be equal to R?
Practically, you want to
For
know...
example, this can be half R, it can be 3/4
No.
R.
But this value will be much smaller than this load resistance. That's why mostly we not encounter this internal resistance. If you buy a battery, okay, so mostly we said that 1.5 volt. The voltage is 1.5 volt. We are not talking about the EMF in this case. We just said that 1.5 volt. It means that at the terminal we get 1.5 volt. Like over here. Over here we get 1.5 volt.
Yeah, we ignore the internal resistance.
Yeah, we ignore the internal resistance because that is too much smaller than this resistance. But if you get this condition, your internal resistance is equal to this, then you will get a maximum power. Then it means practically you will require, this resistor will be very much smaller. Because normally in practically this resistor is smaller, have a smaller value, this resistor have a smaller value. So this resistor, if you want to equalize this resistor with this capital resistor, then it will be smaller. It will have a smaller value.
So this value here is that the internal resistance value.
Yeah, this is the internal resistor. Yeah, that is the internal. That's why I represent it by small r.
But the x-axis is load resistance.
Yeah, x-axis is the load resistor. Okay, I got it. That where is your difference? Here your load resistor is 1 ohm. Here your load resistor is 2 ohm. Load resistor is 3 ohm. Load resistor is 4 ohm. Load resistor is 5 ohm. Load resistor is 6 ohm. Load resistor is 6 ohm over here. So it means that your R is also equal to 6, and that is equal to R. Your load resistance. This axis give you load resistance. Okay.
Load resistance is 6. So R is 6.
Yeah, R is 6 because maximum power. Because in physics tell us that you will get maximum power when your load resistance is equal to small r.
Oh.
Yeah.
But how do you know that's smaller? It's bigger. Like
it is bigger. It is bigger or it is small r. Here I get 5 ohm. So 5 ohm is not a small r. 5 ohm is a big r. 6 ohm is a small r because on 6 ohm I get a maximum power, and 6 ohm is also a big r.
Oh, so this is a rule. Is this a rule?
Yeah, this is a rule. This is a rule. Yeah.
Oh, okay, fine.
Yeah, this is a rule that you will get a maximum power when your internal resistance is equal to external resistance. So
okay.
So this is and
I've never seen this rule before, that's why.
Okay, and this is known as impedance matching. Okay. You know what do you mean by impedance?
No.
Okay, leave it. Resistance matching. This is known as resistance matching. So if you want to get maximum power, then you will apply this condition. If you want to get maximum power, particularly you will apply this condition. You will make sure that your internal resistance must be equal to external resistance. Okay, there is a minor topic, so let's discuss. Okay, so if this is a source, and this source is 2 volt, and there is another source, and this source is 1.5 volt. So what will be your voltage over here?
Wait, what's your question?
My question is, if I connect 2 sources in series, okay, and the voltage of one source is 2.0 volt, and the voltage of another source is 1.5 volt. So what will be my voltage over here?
3.5. Oh, sorry.
Yeah, that is equal to 3.5. Good.
Yeah, that's 3.5. That's 3.5.
Good.
But if it is like this,
Yeah,
then
yeah.
it's 0.5.
0.5, because there is a, if you apply the KVL, so there is a potential drop, then potential rise. So potential drop is 2.0 volt, and there is potential rise, so that should be 1.5 volt, and there is again potential rise, so that will be equal to plus V, potential rise. So your 2.0 minus 1.5 is equal to V, so that is equal to 0.5 volt. Do you get it?
But how do you know that? Wait. How do you know that V is on this side? How, like, why can't it be 2 plus V equals 1.5?
No, here there is a potential drop. This is plus, this is minus. There is a potential drop. So 2, okay. This is potential drop. On left side, I am taking potential drop. This is potential rise. So on on right side, I am taking potential rise. So that is 1.5 volt. That is also right. 2. But this is potential rise. If you bring it closer, then this side is plus. This is minus. So there is a potential rise. Potential rise. So that will be over here on right side instead of taking it over here. This is the potential drop.
It will be V plus 2 equals.
No, it will not be equal to V plus 2. It will be equal to V is equal to 2 minus 1.5.
Oh.
Confused? Okay, I am explaining it again. This is, if battery is like this, okay? And let's say here I have a terminal. So this is positive terminal, okay? Because this battery positive. And over here I will get what?
That's 1.5. Like that.
So, okay. So this is potential drop. So let's say drop is equal to rise.
Yeah.
So this is potential drop, so that should be 2. This is potential rise, so that should be 1.5. And this is also
Plus, yeah, okay, I got it. Thank you.
This is plus and this is minus. Okay, you will take the sign of the greater battery. This is plus and this is minus. So this is drop, rise, rise. So over here you will get rise.
Oh.
So that's really good. Okay, if this battery is like this, then drop. So you will get 1.5. And here there is a rise. So that should be V. So 2 plus 1.5. So that is 3.5 is equal to V.
Yeah.
Okay, so there is a minor topic, that is the potential divider rule and current divider rule.
That's hard. No, the exam questions they give on this topic is so hard. Like, for example, in my exam, they gave like this.
This is too.
You know, in my exam, they gave like this question. Something like this. Look how hard it is. There's 2 sources in one circuit on the opposite direction.
Mm-hmm.
Like, that's so hard. How are you supposed to do that? And then they ask I1, I2, and then I3. I don't even know. I will show you the question. But
okay, so after this question, I think so. This is the last chapter. This is the last. That is the chapter number 13. Okay, and we finished electricity chapters. Okay, chapter 12 and chapter 13.
Yay.
Okay, and after this we will start a new chapter, or we'll do the exam questions.
Exam questions. I sent you a few exam questions on WhatsApp.
Yeah, that were too much easy. So tomorrow we will discuss that exam question. I also send me other questions. Okay, so tomorrow we will cover up all the exam questions.
Yeah, the question I sent you. You can see
you sent me. I saw that questions.
You can see my teacher marked it. So wait, let me see. I got. Wait.
You got samosa and you place samosa on that paper.